Uh, Welcome back to PALS, everyone. We were on a bit of a hiatus with spring break here in Colorado and other things. But today we are back with Bertalan Bodor from Technical University Vienna. He's going to talk about model theoretical tameness and CSPs.
Yeah, so
Please.
yeah, so actually I'm a bit sad that I didn't speak last week because that was also April's Fool's Day. So I don't know, maybe I could have put some joke, but no, it wouldn't work anymore. So no jokes this time. Um, Anyways, so I'm talking about CSPs and some model theoretical tameness conditions. Yeah, so this is joint work with Manuel Bodesca and Paulo Marimon. I'm starting with CSPs, and basically the first half of my talk is going to be a recap of what we know about the CSPs in general, especially the infinite domain ones. And then I will talk about some model theoretical restrictions that we were considering, and then some results and also some ideas for future work. Okay. Right. Okay, so I'm not really sure about the background of people here, so I chose to give even the most basic definitions here. I hope you don't mind. Okay, so what's the CSP? So CSP stands for constraint satisfaction problem, and the setup is that we have a structure B. It's assumed to be have a finite relational signature. And the CSP over this structure B is the following decision problem. So it's a computational problem. And the input is a finite structure with the same signature as B. And the question is whether there exists homomorphism from A to B. Okay, so I didn't actually put this on the slide, but you can think about graph homomorphism problems. So the easiest example is like n coloring, is let's say 3 coloring. That's homomorphism problem to the triangle. You can also encode SAT problems in CSPs and also acyclicity of graphs. The latter is interesting in the sense that then you need this structure B, it's called a template structure, to be infinite, right? So that sometimes it also happens. Okay. Okay, so the relevant notion here is the notion of polymorphisms. So I'm saying that a map is a polymorphism of the structure if it's homomorphism from some power of the structure to the structure itself. By power, I mean this categorical power. So if you haven't seen this definition, basically this is a picture that you have to imagine. That's this one here. So this F is acting row-wise. This is the output. And it's saying that if each of these columns are in some relations, then also the output needs to be in the same relation, right? Yeah, and the reason why this is a relevant notion is that we know that for a finite structure, the complexity of the CSP over a structure is uniquely captured by its polymorphisms, right? Okay, so an observation is that polymorphisms of structure, they always form a clone. So it's called a polymorphism clone of the structure. And so what is a clone? So a clone is a set of operation from some powers of the structure to the structure itself, so that it satisfies two properties. So it needs to contain all the projections. Projections are just these maps that outputs one of the inputs. Here, so this is the ith one. And otherwise, it's close undertaking composition. So this composition means like whenever it makes sense, right? So the arity of F needs to be K, and the arities of all these G's needs to be the same. Yeah. Okay. Okay, so clone homomorphisms. So clone homomorphisms are basically just homomorphisms between clones. So you can imagine clones to be abstract algebras as well, like multi-sorted algebras. So it preserves what you would imagine. It preserves arities, preserves projections, and then composition in this sense. There is also a weakening of this notion that sometimes comes up. That's the notion of minion homomorphism. So I'm only defining this for clones. I don't really need minions in this talk. So it also needs to preserve arities and also composition, but only with projections. Right, so this taking projections is like identifying variables. So basically this is saying that if we're doing this first and then we're mapping the function somewhere, it's the same as if we were doing it the other way around. Right, okay. So if our template structure is finite, okay, so I want to talk about what guarantees that CSP is hard, right? So that's for the finite case, the template structure is finite, and I'm denoting by this P the clone of projections on a two-element set. It actually doesn't matter on what underlying set it lives on, as long as it has at least two elements. Right, and then from some general algebraic arguments, it follows that if this is the whole polymorphism clone of the structure, then the CSP is hard. It's NP complete. Okay. So now the connection you can make using minion homomorphisms is that if there exists a minion homomorphism to pole of A to pole of B, then there is a well, actually like log space reduction from the CSP of B to the CSP of A. And combining these two, we actually get that if there exists a minion homomorphism to the clone of projections, then we know that the corresponding CSP is hard. Okay, so the other notion that's needed here is homomorphic equivalence and cores. So I'm saying that two structures are homomorphically equivalent if there exists homomorphisms between them in both directions. And an easy observation is that if two structures are homomorphically equivalent, then they have the same CSP, just because if there exists homomorphism to one of them, then you can just combine it with this one. Right. And I'm saying that the finite structure is core if all of its endomorphisms are automorphisms. And so in general, it could have more endomorphisms, but they're equal. It's called core. The observation here is that every finite structure is homomorphically equivalent to a core. The reason for that is that you can take the endomorphism of the structure with the smallest possible image, and that's going to be a core, and that's going to be homomorphically equivalent to the original one. So basically, this core assumption is something that we can assume for free, at least for finite structures. Right. And then we have this algebraic dichotomy, stacking and loading all these conditions. Okay, so I formulated this way. If we have a finite core, then these statements are equivalent. Personally saying that there is a minion homomorphism to the projections. Here, the second one is the same with clone homomorphisms, but here we have to add all the constants from the structure. Okay, and then it turns out if these things don't exist, then the polymorphism clone has a Sigur's operation, so it's an operation satisfying this identity here. So I don't know how to draw this lens. And instead of Sigur's, we can also have cyclic. It's also equivalent. Yeah, it's cyclic means that we can shift the inputs in a cyclic way. Gives the same output. Okay, so I already mentioned this. That if one doesn't hold, then we know that the CSP is NP complete, right? And what has been a conjecture for a long while is that on all the other cases, the CSP is tractable as it's actually P. And that's that's a big result that was proven a few years ago independently by Bulatov and Zhuk. And yeah, it says if any of these conditions holds, then the CSP is in P. And this implies that for finite structures, we have a complex dichotomy. So all CSPs are finite structures are either tractable or they're NP complete. Right, okay. So how do these things generalize to infinite structures? Okay, just a small disclaimer here is mostly just a reminder to myself that every structure is assumed to be countable. This is not really a restriction, really, because of Levheim's column or like whatever argument, you can just assume that the template structure is countable. If I forget to mention this separately. And what's usually considered here is a megacategoricity, which has several definitions. So I put here, this is the useful one. This is not, I don't know, in some books, let's say it's mostly a theorem, but we can use this as a definition here. So I'm saying that the structure is megacategorical if its automorphism group has finitely many n orbits for all natural numbers n. Right, so the automorphism group is acting on n tuples, and these need to have n finitely many orbits for all n. Yeah, so this it's a quick observation that this includes all finite structures, although I know that there are some authors that want to exclude them. It doesn't really change anything. You can also see from the definition that this is somehow, because in some sense, it's a straightforward generalization of finite structures. So they're like finite-ish, right? Because we still have this finiteness condition here. Okay, and there are several reasons why we like these structures. So one of them, for instance, is that it still holds that the complexity of CSP over these structures is captured by its polymorphism clone. So this can be saved. Right. Okay, so next, actually, I put these slides in the wrong order, but I think it's fine. Okay, so the next thing is think about how to generalize cores. So actually, we need a bit more. So these are called model-complete cores. And it means that the closure of the automorphism group of the structure is equal to its endomorphism monoid. So closure is understood with respect to the pointwise convergence topology. It's a bit technical. I don't really want to go into details. I just want to remark that in general, we have these two containments, right? So we have the automorphism group of the structure. We have its topological closure. We have so it's here. We have this self-embedding monoid, and we have the endomorphism monoid, right? The last are closed already. So we have to put its closure there. Yeah, and being a model-complete core means that all of these objects are equal for a structure. Yeah, and similarly to what happens in the finite case, we have this theorem. So this is substantially more difficult than the analogous one for finite structures. It says that every omega categorical structure is homomorphically equivalent to a model-complete core. And it's part of the theorem that it's unique up to isomorphism, and it's, again, omega categorical. So because of the uniqueness, sometimes it's just called the model-complete core of the structure. Right, and yeah, basically because of the same reason, this is an additional condition that we can assume for free. Not really, as you will see later in my talk, but that's the intuition basically. Okay, so what is here the source of hardness? It's very similar. Basically, I just added these two words. You need uniform continuity here and here. I don't really want to explain the details here. This is again a bit technical, but yeah, otherwise we have similar reductions here. Okay, and then let's see first how this algebraic dichotomy generalizes to infinite structures, because it does. All right, so the setup is that we have an omega categorical. So now we have model complete core. So that's one change. Okay, so we need to change a few other things in the theorems. So this already mentioned that we need to add this uniform continuity condition here. Okay, the second one is kind of an obvious one. I mean, it's not obvious what to change it to, but you have to change it. We cannot add all the constants, right? But we can add finitely many. So this is like there's a hidden existential quantifier here. So there exists C1, CR, blah, 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 such that this thing, well, actually doesn't exist. That's how the condition is phrased. Yeah, and Sigers, we have to change to pseudo-Sigers. So that's another change. So pseudo-Sigers means it's kind of similar, but we have to compose from the outside by some endomorphisms of the structure. Here it is alpha and beta. Right, and also another change, it's not visible here, that basically there is no analogy with cyclic operations. Somehow that part cannot be saved. Yeah, and the last change is, so now it becomes a theorem that actually we don't have equivalence here. So we know that 2 and 3 are equivalent, and we know that 1 implies 2. But I have to add this remark, is that, so we actually know that 1 is not equivalent to 2, but it is true for, so I put here reasonable structures, which I again don't really want to go into details what this means. So this is some morbid growth conditions. The point is that this equivalence actually holds for all the structures that we will care about. So morally they're equivalent, if you like. Okay, so then what do we care about? Well, okay, so this is the algebraic dichotomy. It generalizes very nicely. And from the, if you go back to the previous slide, just because of this argument, we actually know that if these conditions do not hold, then we know that the CSP is hard. So basically, you want something like if the structure has a pseudo-Sigers, then the CSP is in P. Otherwise, it's NP complete. The problem is that in this generality, we don't even know whether the CSP is decidable, so it could be very wide. So we need further finiteness conditions to somehow make sure that at least the CSP is in NP. Okay, and so the currently standing conjecture in this direction is due to Bolyski and Pinska. And it's saying that if we have a first order reduct to a finitely bounded homogeneous structure, I will quickly explain what these things are. Then we have a CSP dichotomy. And I also put here is that the dividing line corresponds to the algebraic dichotomy. So actually it's saying that if we have pseudo-Sigers, and that's actually only true in this model complete course setting, then the CSP is tractable. Because the other case we already know from general arguments. Right. So the notions here are not super important. I just put this here on the slide. So homogeneity, so that's a well-known notion in model theory. It means that every partial isomorphism, every finite partial isomorphism of the structure extends to an automorphism. So if we have some elements which locally look like the same, then they also look the same globally. Finite boundedness is not so well known. I think it's a bit technical again. It's saying that the age of the structures, age is the finite substructures of the structure, can be described by finitely many forbidden substructures. In general, if you know some homogeneous structures, it's kind of difficult to find one which is not finitely bounded. The first few examples you would think about are finitely bounded. And here I just put some examples as an illustration. So I think everyone's favorite, I'm not really sure, but I guess it's my favorite, skew with the order. And so that's the only infinite dense linear ordering without an endpoint. And then these random structures where the random graph, random post set. Right. And we will see some other examples later. Yeah, and now I realize that actually I didn't talk about reduct. So I put here first the reduct. So this basically means that we start with the structure and then we excuse me, we expand it by some further definable relations. And then we just remove some relations. This is quite general. Okay, so here I put a long list of structures or classes of structures for which this dichotomy has been solved. And actually, I will talk about some of these in the rest of my talk. Basically, I will mention this one, hereditary cellular structures, the Johnson graphs, that's for sure. Yeah, this class will show up, but we won't talk about this result. It's on the list. Okay, so I think that was the recap. So now we're switching to, let's say, the second part of my talk. And that is about, so if you look at most of these results, well, not all of them, but some of them are like, let's consider our favorite structure and then take all of its reducts, right? And then we do the dichotomy for that. So we want to do some general constructions and maybe potentially have some general results. So like taking reducts is quite natural. It's already a formulation of the theorem. So one thing we can do is doing first the interpretations, which is already a big generalization of reducts. Right, okay, so how does this work? So I'm saying that a structure A interprets, let's say first order interprets some structure B. Yeah, and formally it's like this written here. So there is some D, so that and some surjective partial map, which goes from the D power of A to B, so that if we take a relation R of B, and then we pull it back somehow coordinate-wise, so here you can see that these tuples are like tuples of tuples, and then you can make a long tuple out of that. So all these relations, these pullbacks, need to be first definable in the structure A. Okay, so how you can imagine this? So this is a partial map, right? So if you consider the inverse image of the relation x equals x, then basically you can conclude that the domain of this interpretation map, this I, is also needs to be first definable in the structure A. And also it's possible that some tuples are mapped to the same element, but since the inverse image of x equals y is also definable, it basically means that it's first definable that two elements are mapped to the same. Okay, so what I want is to say that basically you can imagine this B as a quotient of some definable substructure of some power of A, so that the quotient, so the equivalence relation that defines the quotient also needs to be first definable. Right. Yeah, and there's just some notations. I of something is structures which are interpretable in that structure, and that structure is going to be just a pure set in this talk or a Q with the order. Right. Okay, so an example for this is one of my favorite examples is the Johnson graphs. So what is this? So the underlying set here is the k-element subsets of the natural numbers. And then basically we have binary relations which are measuring the size of their intersection. Okay, so first observation here is not so difficult. It's like a homework exercise to show that all these graphs are first defined, so first they're interpretable in the pure set. Right. A slightly more difficult exercise would be to show that the automorphism group of this Johnson graph is actually isomorphic to CMOF omega, right? So if we have a, well, actually I change this to omega. How to do this? Sometimes it's omega, sometimes it's n. Okay, so what do I mean by this? So if we have the full symmetric group acting on the natural numbers, it's also acting on K-element subsets, right? So it preserves all these relations as SIs. So that's the subgroup of the automorphism group, and you can actually show that these are all the automorphisms. Okay, so the next statement is a bit more difficult, but it's also true that actually it's enough to take one of these SIs and it can faster define all the other ones, right? So actually we can just drop all of these except for one, and it still has the same automorphism group. In terms of automorphism groups, it doesn't matter which one we take. And another interesting observation is that actually, so I mentioned that we have these actions of CMOF omega on K-element subsets of the natural numbers. So these are all the primitive oligomorphic actions of CMOF omega. Okay. Delete this. Yeah, so in the next few slides, I will talk about the CSP dichotomy for these structures. So that was, if you remember, that was the last one on the list. Okay, so the K equals 1 case, that's just a pure set. So this was actually the first one on the list, and it's an old result by Manuel Bodor and Kara. Yeah, so I don't know his first name. So this is saying that if we have a first order reduct of the pure set, then we have three cases. So either the model complete core has just one element and the CSP is trivial then. And the other two cases, the structure itself is a model complete core. And we have two cases. So either it has a binary injective polymorphism, it's in here. And then we know that the CSP is tractable. On the other case, we know that all polymorphisms are essentially unary, in which case, yeah, obviously there exists a minion, even a clone homomorphism for the projections. We know NP completeness. Right. Okay, so then let's see what happens with the other cases. So first of all, if we just consider the Johnson graph itself as it was written a few slides here, then it turns out that this has an NP complete CSP for K at least 2. But obviously we have other reducts. But what we have shown is that if we take a reduct of any of the Johnson graphs and we take its model complete core, so that's C, then C is actually bidefinable with another Johnson graph. So bidefinability means that we can just reindex the elements and the same definable relations. Yeah, and yeah, so basically this means that if we take a reduct of the Johnson graph, then the CSP is either NP or NP complete. The reason for that, if it's already model complete core, then we know that it's hard because of this lemma. Otherwise, we know what this model complete core looks like, right? So it's bidefinable with this one. And yeah, okay, well, actually we have to argue a bit, but basically you can PP define all the basic relations of the Johnson graph, and by that you can show that we have hardness. Right. So a small comment I put here is that actually in this theorem, I think it's not even possible that this L is strictly between 1 and K. It was not necessary for the results, but just based on some experiments that I was doing, it's probably not possible. Right, so we have the dichotomy for the Johnson graphs. And the next task would be to maybe generalize the dichotomy for everything which is interpretable in the pure set, or maybe over the naturals. Now, the problem here is that neither of these classes are closed undertaking more a complete course. So this is a kind of a problem, because usually the way to solve these CSPs is to switch to the more complete core of the structure and then work over that. Right, so somehow we usually want classes of structures which are close undertaking more complete cores. So somehow this is never an issue. Yeah, so the counterexamples for this. So the second one, it's the easier. So that's the random permutation. If you know what it means. So that's the structure that's a model complete core of something which is interpretable in Q, but it itself is not interpretable. And for the other one, the construction is a bit more complicated. Yeah. So we will not have time to talk about those. Okay, so basically we want something which is robust in this sense. So one option would be to artificially add model complete cores. So we say, okay, we're solving dichotomy for model complete cores of blah 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 blah. So actually, there is a natural class that's it's not going to be this one exactly, but almost. We will see. So there's a natural class that we can put in between these two, and it turns out to be close undertaking model complete cores. And for this, I need to introduce omega stability. So there is a lot of stability notions in model theory. I don't want to go through all of those. And for this one, again, there are several definitions. And I think this is the one. So this one I'm presenting is not the easiest one, but I think this is the most intuitive one. And for this, I need to introduce the Morley rank. And the way it works is that well, there's a typo here. Parameter definable. Yeah, so this Morley rank is actually defined for parameter definable subsets of the structure. And the way it works is that it's at least 0 if the subset is non-empty, and in general it's an ordinal, right? And I'm saying that if it's at least alpha plus 1 if it can be written as a disjoint union of infinitely many subsets, so that the rank of those is at least alpha, right? And for limit ordinals, it's defined in this straightforward way. Yes, and in general, this Morley rank itself might not be an ordinal because it's just from the definition, it's possible that it's bigger than all ordinals, right? And omega stability means exactly that this exists. So this is actually an ordinal. Okay. So maybe I will draw some other picture here. Also put some examples. So the way I sometimes imagine this omega stable structures is that, so we have this structure, right? And we split it up to some parameter definable subsets, infinitely many, right? So we do this, and then we do this again, right? For these subsets. And then we're just continuing this, and basically omega stability means that this process needs to stop at some point, right? So at least one of these subsets we cannot divide further. Right, so the examples I gave here, so basically everything which is interpretable in the natural numbers. Maybe it's not clear from this definition, but yeah, I guess one has to think about this. I guess an easier example is vector spaces over finite fields. So it's an example. And non-example is Q with the order, actually like any structure, an infinite structure which has an order. And the reason for that is that we have this. So this is Q with the order, right? And we can just split this up to infinitely many intervals, right? So all these intervals are parameter definable. And these are, well, okay, so we can choose this interval so that the endpoints are irrational, right? Why not? And then we will see copies of Q with the order here, right? And then we continue this process. It never ends. Right. I'm deleting this. Yeah, and actually I put here a fun fact, and this is due to Shirley and Lachlan Harrington, well, it turns out that all omega stable structures have finite ranks, in fact, right? So this is actually don't have to consider this limit case ever if we're in this context. And so this is a fun fact. The proof of this is the opposite of fun. Actually, it's a very deep theorem. So it's using some, let's say, some classification theorems. Okay, I don't really want to go into the details. Actually, I don't even know it myself. But yeah, so this is a bit easier in our case. Right, and so one of the classes that we might want to consider is this one. So this was actually examined by Lachlan. So I found the paper from the 80s. And what's written there is basically this the equivalence of these first two items. It's written a bit differently, but basically that's the message of this theorem, that if so these two conditions are equivalent. This person was saying that the structure is omega categorical, omega stable, and it doesn't interpret the vectors, any vector space over a finite field. And the other one is saying that the structure is interpretable in Q, but is itself stable. The stability I didn't define, but you can write omega stability here, if you like. So just write omega stable. Right, and basically what also follows from this result is that we can write further equivalent conditions. So I put this one here. So this is saying the structure is omega stable, and it's a reduct to a finitely bounded homogeneous structure. So this this condition here to here, this is exactly the scope of the infinite domain CSP dichotomy conjecture. Right, so these are exactly the megastable structures in that class. And there is also, so if you know about the Ramsey property, we can also add, instead of homogeneous structure, we can add homogeneous Ramsey structure. The reason why this is useful is that we know that this condition, if the Ramsey is here, this is actually closed undertaking model complete scores, and omega stability is also preserved. So for this reason, we know that this class is preserved undertaking model complete scores. Right. So for instance, if you consider these conditions, it's not clear, not close, undertaking model complete scores. The first one, maybe it also follows from that. I didn't see it, but I guess it also follows from that. Okay, and so from this point on, I'm talking about some future research. So so excuse me if the following things might not make too much sense. So this is a potential strategy for solving the CSP dichotomy for these structures. So okay, I didn't introduce the notation, but this D stands for Lachlan's class. So that's the class on the previous slide. And the potential steps are identify the primitive structures, so the structures with the primitive automorphism group in this class. and then solve the dichotomy for those structures. The good news here is that it's not completely obvious. It's also not super difficult to see that primitivity is also something that's preserved by taking more complete scores. So for this reason, we can still assume that our structure is a more complete score, right? Because primitivity is preserved and also this class D is preserved. Right, and then we put pieces together, probably if this is possible. And yeah, from that point on, I have no idea what to do. So yeah. Okay, so what do we have here? Okay, so what about primitive structures in D? So we have seen some examples, right? We have the Johnson graph, right? So then the automorphism group, as I mentioned, it's a primitive action of the full symmetry group acting on the natural numbers on the k-element subsets of the natural numbers. So this is one example. Another one is that is this one. So we take a transitive subgroup G of Sn, right? And we take this wreath product of the full symmetric group with this group G, but its action, but it's we're considering its primitive action. So here, basically, the base set is the nth power of omega, right? And we can act on each coordinate, coordinate-wise, by permuting the elements. And by this G, we can permute the coordinates. Right, so this is what it means, basically. Yeah, and sure, so we can also combine these two, right? So we can take these wreath products, right? So we take the automorphism group of the Johnson graph, and then we take the wreath product of this with any transitive group with the primitive action again. And these are also examples. Okay, so these are actually just the groups, but you can identify the structures from its automorphism group. Okay, and the comment here is that we believe, first of all, that these are all the primitive actions. So we have a primitive structure. These are all the possible permutation groups. Excuse me, automorphism groups. Yeah, okay, it's a bit difficult to say why we believe this. We have some strong results by Lachlan, and we kind of believe that we can conclude this one, even though it's not stated explicitly. And we also believe that all these structures, they have hard CSPs, except for the pure set, right? So for the pure set, it might have this injective binary polymorphism, and then the CSP is easy. Right, so this is for primitive structures. Okay. And I have this penultimate slide, and it might not make too much sense what I've written here, but basically one rough idea is that in the general case, we pick some maximal zero definable equivalence relation and then take the quotient, right? So that's C. And then we solve the CSP using the CSP of this quotient structure and then the CSP of over one of these parts, or we show hardness, whatever follows. Right, and then maybe we use some induction. Okay, so the most problematic point, I already put this here, is that, so I assume that this E to be zero definable, but it might not be preserved by polymorphisms, that is to say, it might not be PP definable. And yeah, so this is where I want to mention this result of mine. That so this is what I did in my PhD dissertation. So this is I proved the CSP dichotomy for hereditary cellular structures. So the definition is a bit tricky, but basically based on what I introduced so far in this talk, you can imagine this structure to be omega stable, plus the condition that that all these levels, all these primitive structures that show up, they are either just a pure set or finite structures, right? So I put here that this idea partially works for hereditary cellular structures. So it's an inductional argument. And sometimes I can take advantage of the fact that if this that this is PP definable or preserved by polymorphisms. If it is, sometimes it isn't, and yeah, then you have to think. There are some parts of the argument which don't seem to generalize, like even in this context. So I'm not sure if this is the right way to approach this, but maybe it is. Yeah. Okay, and one last thing I wanted to mention here. So this is mostly targeted towards experts because it needs the notion of canonical pseudofigures, which I don't want to introduce. But basically, so we know that if there is no pseudofigures polymorphism, then the CSP is hard. And this pseudofigures with this notion of canonicity property, it actually means that it actually implies that the CSP is tractable. So this is some equivalence that would imply the CSP dichotomy. So actually put this here, right? And we know that this is very rarely true. So we have a lot of counterexamples. There was a point where I thought that somehow the order is the thing that somehow makes this not work, but there are some other examples, this hypergraph example. And the order is, you add the order and it's not even there, but somehow causing troubles. This is true for hereditary cellular structures, and it's also true for some of these other cases, so the Johnson graphs, for instance. I mean, in that case, it's for kind of trivial reasons because all the new CSPs are hard, right? So basically, this is not saying anything in that case. But yeah, as far as I know, this still could be true for omega stable, omega categorical structures. Right. Okay, and I'm finishing my talk with this very nice diagram, which is due to Manuela Bodieski. So here you can see a lot of classes of structures can be relevant. Well, it could be like some of these containments could be interesting just from a model theoretical point of view, but also from the CSP point of view. So what I talked about in this talk is this one. This is what I started with, right? And this is Lachlan class here. And this one on the top, this is the structure for which the infinite dichotomy conjecture is stated. And there's some other ones I didn't talk about. Yeah, that's all. If you have questions, please.
Well, thank you.